On the 2nd of July, 1909, in a laboratory in Karlsruhe, two men sent by a chemical company stood watching a steel tube about the size of a rifle barrel. A seal blew. Nothing came out. They went to lunch.
And when they came back?
Ammonia, dripping into a glass, about a cupful over the next couple of hours, of something that smells like floor cleaner.
A cupful. That tube is the reason roughly half the nitrogen atoms in your body are in your body at all.
Stand in a field. The column of air over 1 hectare of that soil holds roughly 78,000 tons of nitrogen. It is the most abundant thing in the sky, and the wheat underneath it is starving for it.
Why can't the wheat take it?
Because nitrogen in air comes in pairs, and the two atoms are locked together by a triple bond. 945 kilojoules a mole to break it.
Which is what, and something I can picture?
Lightning. A bolt tears a few of those pairs apart, and the rain washes the pieces into the ground. For 3 billion years, that was one of only 2 ways it happened here. The other is bacteria in the roots of beans and clover, doing the identical job at the temperature of wet soil.
So farming was borrowing. You carry the nitrogen off the field and harvest and wait for lightning and clover to pay it back.
Which is why ships sailed to islands off Peru to dig out bird droppings 30 meters deep. By the 1870s, the Chincha Islands were bare rock. In 1898, William Crookes told the British Association that the bread-eating nations faced famine unless a chemist learned to pull nitrogen out of the air. Here is the entire reaction. 1 nitrogen molecule, 3 hydrogen molecules, and out the other end, 2 of ammonia. 4 molecules of gas go in, 2 come out.
Fewer than you started with.
That is the first lever. Squeeze the gas hard enough, and the side that takes up less room wins. So you run it at around 200 atmospheres, the pressure 2 kilometers down in the ocean, inside a pipe, all day. The second lever runs the wrong way. Making ammonia gives off heat, about 92 kilojoules a mole, and a reaction that gives off heat is discouraged by more heat. Cold would give you a beautiful yield.
So run it cold.
Run it cold, and you will wait longer than the universe has existed. The bond does not care about your yield. It cares about being hit hard enough to break. So the temperature is a bribe, about 450 degrees, hot enough that anything happens at all, cool enough that the ammonia does not immediately come apart again. And the man whose principle that is nearly got there first. Henri Le Chatelier tried this reaction in 1901. Air leaked into his apparatus, it exploded, and it nearly killed his assistant. He abandoned it, and later called that the greatest blunder of his scientific career. Pressure and heat are not enough. You need a surface that grabs a nitrogen molecule and holds it while the bond is prized open. Haber used osmium, one of the rarest metals on Earth. BASF quietly bought up nearly the entire world supply, and it still would not have been enough to fertilize a county. So the company handed the problem to Alwyn Mitesh, and he did something no academic would have had the patience for. He ran more than 20,000 test runs, feeding candidate after candidate into small pressurized tubes, looking for anything cheap that worked.
And the answer was iron, which is where every textbook stops. But plain iron is nearly useless. The samples that worked were the contaminated ones. Magnetite ore out of a Swedish mine outperformed the purified metal, and it took years to work out why.
2 things nobody had put there. Aluminum oxide, which acts as scaffolding and stops the iron clumping shut into a dead lump at 450 degrees, and potassium, which loosens the iron's grip on its own electrons so it can pull harder on the nitrogen.
A century of chemistry, and the recipe is still rusty iron with impurities in it.
Everything so far is what a diagram tells you. Pressure, heat, iron, which leaves the question the diagrams never answer. Of all the gas that goes into that vessel, how much comes out the other side as ammonia?
Half at those pressures.
15%. On a good day, 20%.
So it mostly does not work.
It mostly does not work, and that is the design. The gas leaves the converter still 85% unreacted, and instead of throwing it away, you chill the stream to around -25 degrees. Ammonia liquefies. Nitrogen and hydrogen do not. So the product drains out of the bottom as a liquid, and the failures get pumped straight back to the front of the converter and pushed through again. And here is the trick inside the trick. By pulling the ammonia out the instant it forms, you never let the reaction reach the balance point that limits it. It is always chasing a product that keeps disappearing. Round the loop enough times, and better than 97% of the gas ends up as ammonia.
So it's not a reaction, it is a circuit.
With one leak on purpose. Argon comes in with the air, never reacts, and would slowly choke the loop, so a thin stream is bled off forever.
So they choke it on purpose.
A cupful in a laboratory is not a factory. Haber's tube was hand-built by an English assistant, Robert Le Rossignol, who had to design his own valves because nothing sold anywhere could hold 200 atmospheres. Scaling that up fell to Carl Bosch, and it broke immediately.
Broke how?
The steel dissolved from the inside. Hydrogen at that pressure and temperature does not sit politely in the pipe. It works into the metal, finds the carbon that makes steel strong, and pulls it out as methane. The wall turns brittle and hollow. Bosch's first converters split open after less than 80 hours.
You cannot make the pipe thicker. Thicker steel has more carbon to lose.
So he built two pipes, an inner liner of soft, low-carbon iron with almost nothing in it for hydrogen to steal, and around that an outer steel jacket doing all the pressure work. And then the part that sounds like sabotage. He drilled holes through the outer jacket.
Holes in the wall of a 200-atmosphere vessel.
Narrow ones, so the hydrogen that seeps through the liner escapes instead of building up and bursting the shell from within. They are still called Bosch holes. The first plant opened at Appau in September 1913.
And almost none of the first output went onto a field.
No. The same chemistry that feeds a plant also feeds a shell. Ammonia oxidizes to nitric acid, and nitric acid is what you need for high explosive. In 1914, the Royal Navy cut Germany off from Chilean saltpeter, which was where every European army had been getting its nitrates.
How long could they have kept fighting?
Historians generally put the stockpile at somewhere around 6 months. The war should have run out of ammunition in the spring of 1915. Instead, Bosch went to the War Ministry and promised that BASF could make nitrates from air. Government money followed. A second and far larger plant went up at Luna, and the shells kept coming. Haber went further than that. On the 22nd of April 1915 at Ypres, chlorine gas was released from cylinders across a 4-mile front, and he was there in person supervising it. Days later, his wife, Clara Emerwar, a chemist herself, shot herself with his service pistol. You will hear that framed as a protest. The documentary evidence for why she did it is thin, and honest historians say so.
And in 1919, they gave him the Nobel Prize for Chemistry anyway.
Run the machine today, and one question is left. Where does the hydrogen come from?
Water, presumably.
Natural gas. Methane and steam over a nickel catalyst at around 800 degrees, which strips hydrogen off the methane and leaves the carbon behind as carbon dioxide. Most of the energy in the whole process is spent there, making hydrogen, not squeezing it. Add it up, and ammonia synthesis burns somewhere between 1 and 2% of all the energy used on Earth.
And it was never the only way to do it. Norway was already fixing nitrogen in 1905, blowing air through an electric arc powered by waterfalls. It worked. It just needed so much electricity that it only made sense next to a hydroelectric dam. Haber and Bosch did not make nitrogen fixation possible. They made it cheap.
Cheap enough that around half the nitrogen atoms in the average person's body were fixed in a steel tube rather than by bacteria, and cheap enough to overshoot. Less than half the nitrogen spread on the world's fields is taken up by the crop. The rest runs into rivers and feeds algae instead, which is why there is a low oxygen zone the size of a small country in the Gulf of Mexico each summer. The strangest thing about it is how little of it is clever. A bribe on the temperature, iron that has to be dirty to work,
holes drilled in a pressure vessel, and a loop that fails 85 times in 100 and simply goes round again.
There is a version of this story where the man who solved hunger and the man who supervised the gas are not the same person.
There isn't. That is the one we have.